So moving forward with our next presentation, titled Fire Impact of Vehicles, Fire Exposure on Polymer Concrete Overlays. Our speaker for this presentation is Shunani. She is Assistant Professor at University of Maryland in the Department of Fire Protection Engineering. She received her PhD degree at Texas A&M University in 2018 and her master's degree at Tonjai University in 2013. Dr. Nee's research focuses on structural fire engineering, fire forensics, impact of fire on civil infrastructure, and fire safety of tall mass timber buildings. Her research has been funded by the National Institute of Justice, Fire Protection Research Foundation, University Transportation Centers, and Grants Program at the University of Maryland. So I call upon Dr. Shunani to present her presentation.
Hi everyone, I'm Shunani. I'm I was working for the Department of Fire Protection Engineering. And this is a project which I was done when I was still working for Utah State University, and it's sponsored by the University Transportation Center. And we study the impact of vehicle fire exposure on the polymer concrete overlay. So the polymer concrete is increased use in highway structures and as the overlay to protect the concrete bridge decks due to its good performance, such as good resistance to salt and water, high chemical stability, and strong compressive strength. While the polymer binder, it decomposes at high temperatures, while the vehicle fire is prevalent with, even in the 2019, and there were more than 223,000 vehicle fire was reported, and more than 180,000 was occurred in the highways. And nowadays, the number of EV was increased, and on the roadways. So, and the EV have one problem: it's very difficult to extinguish it, and the fire lasts much longer compared to the traditional vehicle fires. So, there's our imperative need to study the impact of vehicle fire exposure on the polymer overlay, and to guide the future overlay material design and constructions. So the goal of this project is to study the impact of vehicle fire exposure on the performance of polymer concrete overlay. And in this project, we construction reinforce a concrete slab, and we construction the polymer concrete overlay over the concrete slab. And we do a realistic vehicle fire tester in the firefighting training center in Logan, Utah. And then we do some pre-fire and post-fire performance test of the polymer concrete overlay. So this is a bridge deck. It's a concrete panel. We try to replicate a bridge deck, and it is 36 feet by 20 feet. And this is the overlay, and the polymer concrete we use is polyester polymer concrete (PPC). And before the construction of the overlay, we grade the concrete surface, and then we apply the primer coating, and then we apply the PPC mix, and after that we apply the finishing sander. And the thickness of the polymer overlay is 0.94 inch on average, which is greater than the minimum thickness required by the Utah Department of Transportation. So this is the instrumental plan for the slab, and we have attached thermocouple in the interface between the overlay and the concrete slab, and also we have attached the thermocouple over the surface of the overlay. And this, after that, we put the vehicle at the center of the slab, and those are the instrumental plan of the vehicle fire tester. And we have thermocouple inside the vehicle, and around the gasoline tanker, and below the vehicle. And also we have a couple camera to recording the burning process of the vehicle. And we have also have two heat flux sensor, which is at the back side of the vehicle, and the other one is at the side of the vehicles. in the tester, at the beginning of the tester, we have left 2.4 gallon of gasoline in the oil gasoline tanker in the vehicle, and then we around that gasoline link it to the slab and then ignite it. It's basically to replicate the corrosion, the vehicle corrosion leading to the gasoline tank, and then which leading to the burning of the vehicle, which is very common in the real vehicle scenarios. And the vehicle fire was burned for 225 seconds, and it is stopped early than we expect because there's a jet flame from the gasoline tanker. Under the high temperature, the gasoline in the tank was evaporated, and then due to the high pressure in the gasoline tank, there's a jet flame, and which considers a safety issue where the firefighter stopped the fire early than we have designed. But the total the fire was burned for 225 seconds, and in the tester we can observe the direct burning flame contact of the slab, so overlay to the frame, and due to the linkage gasoline over the surface, and also during the tester, because the vehicle have a lot of plastic materials, and those material melts and fall down on the slab surface, and which also have the direct flame contact with the slab. So this is the image shown in the right side as is the process of the vehicle fire tester burning, and the one which the plot which is shown at the bottom side of what is the vehicle after the burning, and it's basically complete burned, and but the engine compartment was not burned, and the majority fire is at the back side and the passenger compartment and the driver compartment. So this is what we measured during the vehicle fire tester, and the left plot shows the heat flux we have measured. So the maximum heat flux at the vehicle size, and which is 74.5 kilowatts per meter, which is relatively high. And the other heat flux sensor at the back side of the vehicle, which is 26.7 kilowatts per square meters. So imagine that if this happens in a cable bridge, right? There's a steel cable around the vehicle, and such a high heat flux will leading some issue to degrade the steel strength of the cable, and which may endanger the bridge. And also we have recording the temperature in the vehicle, and the maximum temperature which we measure inside the vehicle is almost 2,200 Celsius degree, and which is measured inside the vehicle is the compartment fire. And we didn't measure the external flame because it's external fire, so the temperature will not reach to 1,200 Celsius degree. But what I found from the literature, it should be like some kind of like 700 degree, even the external flame. So if this vehicle is not under the bridge deck, if it's below the bridge deck, such a high temperature will leading some issue to the steel bridge or composite bridge deck. So this is the temperature we measure over the surface on the overlay. And this is the temperature, the peak temperature we measure is 744 degrees Celsius degree, and which is close to the vehicle, and this is because the liquid gasoline directly burning over the surface, and that's the high peak temperature we measure. And in the tester, we measure two peak temperatures. The first peak temperature is within the 100 seconds. It's because initial gasoline ignition and also due to the burning plastics. And the second peak, which is around the 190, 89 seconds to 270, 47 seconds, and which is due to the vehicle fully igniting and also the jet flame from the gasoline tanker. So in this part, in the right plot which I have circled, this is the area which is very close to the vehicle and which is exposed to the most highest temperature during the vehicle fire test. And this is the interface temperature we have measured during the vehicle fire test, and the interface between the concrete slab and the polymer concrete overlay. And it's still relatively low during the test. And one thing is because the protection of the overlay have relatively low thermal conductivity, and which protected the interface. For another thing, if the vehicle fire can extend it further, and like EV fire, electronic vehicle fire, it can extend it for more than 1 hour. It will be ignited again and again. So we can imagine that even the interface temperature will increase significantly if it's extended to longer fires. And although it's only the maximum is only 55 degrees C, but the overlay concrete have a relative large thermal expansion coefficient. The thermal expansion coefficient between the polymer concrete and the concrete are relatively different. So the thermal expansion may still will lead into some delamination from the between the overlay polymer concrete overlay and the substrate concrete. So this is a slab after the vehicle fire test, and we wash it to make it look better. So we found that the finish sander because all the overlay have the finish sanding on the surface, and we found the finish sander on the polymer PC overlay surface has peeling due to the polymerizance degradation and the water flushing. And also some areas, especially those areas under the vehicle, and some of the areas of the slab experience the thermal decomposition and resulting some charge surface. So this is after the vehicle fire test, we collect a sample almost over the whole slab surface and to do the post-fire performance test to measure its bond strength, rapid chloride penetration, resistance, surface hardness, and also we do the bond strength test. We measure the delamination by the IR camera. So those are the results about the scandal resistance, surface hardness, and abbreviation resistance and chloride penetration. And what we found is that for the average, if we consider the house slab, the average temperature is 233 degrees. The temperature increase is 233 degrees C. So and the scandal resistance was reduced by the 90.3%, and the surface hardness was reduced by 7.3%. And if we just look at those areas which exposed to the high temperature, and the resistance was reduced, ranging from 33.3% to 23.1% for the different type of performance. And if we look at the peak reduction, and we can find the range is from the 30.2% to 45.6% for the different type of performance. And those are the results for the bond strength test. And before the fire, and we do five tests, and 4 of them was filled in the substrate concrete, which means the slab, the overlay, and the concrete have a relative good bond strength between the concrete substrate and the overlay. And after the fire, we basically tested the bond strength test over the whole slab, and especially in those areas which was exposed to the high temperature, and we found that majority of them was filled in the interface. So this is the water penetration, water permeability tester, and because the water permeability penetration test is very sensitive to the concrete composition, right? So in order to reduce the uncertainty, we try to test the water penetration for one sample before the fire and after the fire. So instead of using the sample directly from collected after the vehicle fire tester, we have before the fire we have collected a couple samples, and we measure its water permeability, and then then we expose those samples to a relative high temperature, and we consider 550 degrees C, and we also expose some sample to 700 degrees C, and 700 degrees C is almost the peak temperature we have measured over the slab surface during the vehicle fire test. And we expose those samples for 60 seconds and 180 seconds and 300 seconds at the heating rate of 3 degrees C per second, which is the heating rate we have measured during our vehicle fire test. And we do this for the sample before and after fire, and we found that as the temperature increased, the water permeability increased significantly. And similar to the duration, when the duration increased from 60 seconds to 300 seconds, and also the water permeability increased. And for example, if the sample was exposed for the 700 degrees C for 300 seconds, and the water permeability will increase by 370 percentage. So those are the delamination tests. We're using the IR camera to capture the slab surface and in the afternoon time during the summer. And then before the fire, we take the thermal image over the whole surface, and also we do the similar work after the vehicle fire test. And we found that even before the fire test, there's some hot spots, but it's only at the location 60. And after the fire test, especially for those areas which exposed to the high temperature, and a lot of hot spots was identified. So this is the conclusion for this study. So basically, this study was explored the effects of vehicle fire on civil infrastructure, especially on the polymer concrete overlay for the bridge deck. And we did a vehicle fire test to conduct on a reinforced concrete slab with the PC overlay. And the maximum temperature reached was 102,000 degrees C for the vehicle. And this is a compartment fire inside the vehicle. And over the surface at the maximum temperature we have measured is 745 degrees C. And the highest heat flux around the vehicle was 47.5 kilowatts per square meter. And this have leading some issue. If there's this high heat flux from the vehicle fire can damage the surrounding infrastructure, cable bridge and the cable for the steel bridge. And for example, if the fire was happen in the near wilder areas, and such a high heat flux may potentially will ignite it, and then leading to some wildfires as well if this bridge was in the wildland areas. And also the rising number of the EV, and which increases this risk because they are long-lasting fire. It's difficult to extinguish them by water, and sometimes you extinguish and then the thermal run will begin. The battery thermal run will begin. So start again. So the fire will start again and ignite it and extinguish, ignite again. So leading to the fire have a relatively longer period compared to the traditional vehicle fires, and which will definitely have significant potential damage to the civil infrastructure. So even in our test, the vehicle only exposed was last for 225 seconds, but even such a short exposure to high temperature, it's already damages the PC overlay property significantly. So it impacts scan resistance, surface hardness, abrasion resistance, water permeability, and chloride penetration resistance, and also increases the overlay delaminations, especially in those areas which is exposed to the high temperature. So the boundary strength tester, even though we do the delamination test by the some IR camera, but we didn't, we didn't jump samples there to see whether that delamination happens. But we do the boundary strength tester, which in some way was confirmed that the significant bound failure in the high temperature areas. And so we needed to design some measures to reduce the temperature exposure or slow down the degradation of the polymer concrete overlay, and which is important. For example, you can add some fire retardant material in the polymer concrete materials. This is maybe a strategy we can try. That's all. Thank you. Any question?